So, to remind you what we were looking at, we said we have some physical process, let's say, which contains a dependent variable A, which is a function of several independent variables A1, A2, etc. Let's say AK plus 1, etc. AN. Okay, and the system has K fundamental dimensions. And then we said we will use a system of units A1, A2, etc. up to AK, in which case we can write each of the quantities, let's say A, as A1 to the power M1, A2 to the power M2, etc. AK to the power Mk is a function of A1, A2 and so on up to AK plus 1 by A1 to the power P1, A2 to the power P2, etc. AK to the power Pk and so on, An divided by A1 to the power R1, A2 to the power R2, etc. AK to the power Rk. So this is what we ended up yesterday. So what did we have? We originally had A as a function of several independent variables, and we selected a system of units which is given by a few of them. So we had K fundamental units. So we have taken K variables and we expressed all other variables in terms of that K variables. Okay, and that's all the proof is, because each of these quantities now you have entered up are non-dimensional numbers. Okay, for example, this, let's call it pi. This will be pi 1 and so on, and there will be, this will be the pi n minus k, because there were n minus k independent variables left. Okay, so essentially you have ended up by saying that pi is a function of pi 1, pi 2, etc. up to pi n minus k. Okay, or one another way of looking at is, if your function originally was f of a1, a2, etc. up to an is equal to 0, you would have equivalently written it as also a function of pi 1, pi 2, etc. up to pi n minus k equal to 0. So that's what essentially the Buckingham pi theorem is. Is it clear? Any doubts? So if you have n variables and k dimensions, you find out n minus k independent n minus k dimensionless groups. And I want to tell you something else, and that's actually a story. Okay, it's a story that typically goes with Buckingham pi theorem, actually dimensional analysis. The story that we may see is almost true. Okay, I think over a time it has got lots of spices into it. But still, I think it's overall a good story to see it. So let's see. Okay, so it's there you go. Okay, so Trinity test actually is a code name. Okay, it was code name of the first nuclear bomb that was tested. So now, I mean, nuclear reactors and everything is very common. But long time back, that's 1945. When actually this test was held. This was held in, right now it's in Mexico, in a place, okay. You can see it's, in fact, these all things are taken from Wikipedia. You can read more about there. It says that it was in, on 16th of July at 5:29 a.m. this happened. Actually, it was held, or it was supposed to happen at 4 o'clock because of rains. Then it was moved to 5:29. Now all these details are precisely given. Okay, and that actually shows how important this test was. We'll see why this test important was. And the right hand side that you're seeing is just a board that you will see if you go there at the moment. Okay, it's a protected site. Let's see a video of what this test looked like. So this is shot from a distance of almost 10 kilometers away from where the test was actually happening. Okay, 10 kilometers is quite far, you can imagine. Did you see that explosion? You saw something, right? So there, I think it's better now. So imagine you're seeing it 10 kilometers away from where you're sitting. And it's that huge. The huge fireball that rises. This is a close-up of near to the ground. Here you will see the top portion. So what is the big deal about the test? Okay. So the point is that before this test, the world had never seen something called a nuclear bomb. Okay. So people had developed nuclear reactions and so on. Some theory was available. Then theoretically it was found that it is possible to make a nuclear bomb. Okay. But how strong is the theory? Will it actually happen? So this was the time of Second World War. So now, why this story at all suddenly? Okay, there is a famous name associated with it, and that is G.I. Taylor. We have already heard this name, right? When we talked about Taylor Cuet flow. This guy was a fluid dynamicist. He is famous for several things that's in fluid mechanics. So you heard about Taylor number, Taylor Cuet flow. Okay, there are lots of other things like Taylor's instability, Taylor vortices, Taylor scales, and so on. Okay, so a lot of things he has contributed. So what he said is this: look, what is bomb? It's basically a release of energy. A lot of energy that was concentrated at a particular place essentially gets expanded to a large amount. Okay, there is a wave of energy that's going to come spherically in all directions. That's what for him the bomb was. So he said, okay, if that's the case, let's write down what might be the relevant variables involved. And that's the first step of doing non-dimensional analysis. So let's see what are the variables that he considered. He said energy, okay, because energy is very concentrated and it's going to be released in a spherically symmetric form. So let's say E, the total amount of energy involved, is one of the variables that we want to worry about. So that's E. Then R, the radius of the fireball, which is getting expanded. Okay, and he definitely wanted to know how fast it's going to grow and how much it is going to grow. Okay, so R is the radius of the fireball, T is the time, okay, over which this is happening. Then he said there is a huge pressure that's going to be developed in the fireball, right? Which is what is going to expand the whole thing, and it's going to work against the external pressure. So he said, okay, let's consider the pressure inside the ball and the pressure outside the ball as two relevant parameters. And he also said we'll also worry about the density of air. So the density of the air is going to be so it will be a superheated air. Okay, so you're going to consider the density of that, and you're going to consider the density of the outside fluid against which it is expanding. Okay, so this is because it's really that this high pressure is working against the atmospheric pressure to expand it. So that must be the mechanism that is controlling how fast it is going to expand. So let's say if these are the variables involved, then what could be the relation that exists between these variables? Now you know how to do that because you know Buckingham pi theorem, or you can use Ipson method. Find out what is the non-dimensional number, what are the non-dimensional numbers that are gonna come up. So that's the way Taylor chose to represent, but you might probably get some combinations of these. You can actually verify that as we said, it can be represented in many ways, okay, depending upon what you choose as your repeating variables or what you select as your fundamental dimensions, you will get different combinations, but they would represent the same thing. So if you are getting, let's say, pi 1 and pi 2, okay, if you combine pi 1 and pi 2 in some particular fashion, you are going to get the same non-dimensional number that he has written there. So he got these four of them, okay, pi 1 is some e t square by rho 0 to the power minus 1 by 5. Then there was a pi 2, a pi 3 and a pi 4. And of course, as we have been saying, there exists a relation between these four, and that's what he wrote. And that's not surprising to you anymore. Now since he found that these four, okay, then he had to make some conclusions out of it. So he thought what could be the best thing that he can do. And he said, okay, let's look at some of those non-dimensional numbers. There involved a non-dimensional number that was ratio of the densities. Okay, so if you basically say, look at it as density of air, outside air, by density of that fireball, that's going to be extremely small. Okay, because you have large amount of gas in a small amount of space. So is pressure. Okay, so two non-dimensional groups are going to be extremely small. And he also said, look at this pi 2, one of the non-dimensional group that he got, which actually had this particular combination. And he said he would look at things when time is very small. That means at the very beginning of the explosion. Okay, so this is t to the power of 6. That means it's going to be extremely small quantity. So in other words, what he said is that I look at that situation in which pi 3, pi 4 and pi 2 are very small. Okay, if you do that, then originally you had pi 1 written as a function of pi 2, pi 3 and pi 4, and now you are saying that you are going to make pi 2, pi 3 and pi 4 very small, or in other words, that would amount to say that pi 1 is some function, okay, which is not dependent upon anything else, okay, and therefore pi 1 is a constant, okay, or some number, whatever it is. So pi 1 was this expression which contained radius, e, t square and so on. See, he wrote it in a nice form. Then that e is some constant times rho 0 times r to the power of 5 t to the power of minus 2. Alright? Okay. So where k would be some constant which we do not know what's going to come out. Or if you rewrite this equation as r as a function of t, which of course you can do, you will see that r is a into t to the power of 2 by 5. Okay, so he said that is how basically the radius of the fireball is going to grow. Okay, it will grow with time as a function of 2 by 5. At least at the very initial moment wherever he could neglect other non-dimensional numbers. Now the test happened. In fact, he witnessed the test also, but he did not get the details. Okay, he had no idea about the numbers, so he could not actually verify any of the calculation. And then in 47, okay, there was a magazine called this magazine, okay, Life magazine, which carried an article, okay, about this Trinity test, or the pictures that were released were of this form. Okay, so basically you see the explosion, and that was enough for Taylor because there was a length scale and a time scale present in that photograph. You see that? Okay, in fact, the magazine actually contained a series of them in which it said, see, at 0.10 milliseconds, this was the how it looked like, and then it had information up to 1.93 milliseconds. So he got basically time and radius. Okay, and that's all he needed. He went back to his equation, okay, which, so you had derived that R is a function of some constant which is basically dependent upon other quantities, t to the power of 2 by 5, where this constant A will now contain what is the amount of energy that's involved, right? So he fitted R versus T, calculated A and calculated E, okay, the energy of the bomb, which was actually a classified information there. Okay, nobody knew, but he calculated, and then so the graph actually, because of this incompatibility, didn't come well, but so you can see the data points. It came out to be a very nice straight line, okay, falling on t to the power of 2 by 5. Okay, and then he back calculated what is the energy, and this is the number that he came up with. Okay, and in fact, it happened to be very close to what was actually used. Okay, so that's the strength of non-dimensional analysis. Okay, without knowing anything, you could still calculate some very relevant information. Okay, so this is, I thought I'll show you some pictures of the classic problem that we have been considering. Okay, I've been telling that, okay, let's see, we have a fluid, that is flowing past some object, and we have been thinking about, how to calculate the force on that object and so on. These are from some experiments, okay, some experimental pictures. And the way people do it, I think I mentioned sometime, you just put some particles into the fluid and look at the motion of the particles. That would tell you how the fluid flow is going to look like. Here you have this circle is actually a cylinder. So you have a cylindrical object. Fluid is flowing from one side and it's going to the other side. It's in this picture, it's not obvious, but here the fluid is coming from the left side. It basically, deflects and then it goes back. Okay. So these lines would be, what lines these would be? Yeah, these lines are streamlines in this particular case. Okay. These are streamlines, and this is at a Reynolds number of 0.038. Okay, very small Reynolds number. This is how you would see flow past a cylinder. Okay. This is even at a slightly higher Reynolds number, and you would see something very similar. Reynolds number is actually 1. This is Reynolds number is equal to 19. Okay, when Reynolds number increases, what happens is that the fluid is actually coming from the left side of your screen, yes, and then it goes, and then these circulations will develop at the rear end. Okay, on the back side. Okay, these are called vortices. Okay, and there is a lot of, there is a strong fluid flow. Okay, that means you actually lose a lot of energy because of the formation of this. We'll see that later. So that's what it would look like. Here is another picture which is even at a higher Reynolds number. So it basically comes and then it goes, and these vortices actually become bigger. Okay, these circulations. And if you increase the Reynolds number further, which is 55, these vortices will actually dislodge from the cylinder, and then it will actually start going away. Okay, so this is some picture of that, and you can see that initially when flow was very neat, there was nothing that you were losing. Okay, but now you basically have a large region with lots of vortices or very circulating region, and you are actually going to lose a lot of energy because of this particular process. Yeah, so that's what flow past an object would look like. Okay, and we know that you can actually calculate the force exerted by that object simply as a function of Reynolds number, and what you see is essentially that graph. Okay, on the left hand side, it's called the drag coefficient. It's the force. I think I should be able to write. Yeah, So it's that drag force that we calculated over rho u square L square, okay, versus Reynolds number. That's how you get this plot, and this is actually a plot that you get when whatever experimental observation, whatever simulation you do, you can actually put it into the single line. Okay, so there are two things that you see. One is that of the sphere and one is that of a cylinder. Cylinder and sphere are two different objects, so the curves would be different, but you can see that it is giving you a nice plot. We still don't know how to calculate this theoretically. Okay, there is no way you can calculate it except in some limits. But so this is a very important curve, and you can see that as you change the object, you are going to get different curves like this. So this is a way of representing it. So here the flow is laminar. Here the flow is laminar. Here also, actually the flow will be laminar. It would just be that there will be lot of circulation. There will be lot of vortices like this, but that doesn't mean that the flow is turbulent. Okay. Here also, I think the flow will remain turbulent. By the time this reaches, there is chances that some turbulent, flows will develop in between. The outside fluid will still continue to be laminar. Okay, and remember that 2100 has nothing to do with this particular case. Okay, here you can see that the Reynolds numbers are much smaller. Oh no, this is a different transition. This is a transition called turbulent boundary layer, which is not the Reynolds number at which it happens. So what happens is, which you will see, this region which is very close to the surface, okay, we would expect the flow to be laminar, right? Because it's very close to the surface, there will be lot of friction coming from the surface, the velocity will be all smooth. But beyond some Reynolds numbers, actually even that region will become turbulent. So the region which is very close to the surface will become turbulent, and that happens at that particular Reynolds number. And this is just formation of vortices.